This is section 9.6, Other Angles of a Circle. So far, we know how to find the measures of a central angle. Remember, a central angle is an angle whose vertex is the center of the circle. We know how to find that measure. That measure is the measure of the minor arc. We also know how to find the measure of an inscribed angle. Remember, an inscribed angle is an angle whose vertex is on the circle and whose sides are chords of the circle. That measure is half of the measure of the intercepted arc. And we know how to find the measure of an angle formed by a chord and a tangent, which is also half the measure of the intercepted arc. But there are a bunch of other angles that we can form with circles. So what about angles formed by the intersection of any two chords? So the intersection point may not be the center of the circle, so we may not have a central angle. How do we find the measure of those angles? So I've drawn two chords here in my circle. They intersect in a point. That intersection forms two pairs of vertical angles. But how do I find the measures of those angles? Or how do the measures of those angles relate to the measures of the four arcs of the circle that those chords make? Well, here's a theorem that explains all of that for us. The measure of an angle formed by two chords that intersect inside a circle is equal to half the sum of the measures of the intercepted arcs. Half the sum of the measures of the intercepted arcs. So, for example, in the picture I've drawn here, we've got angle 1. Angle 1, according to this theorem, is going to be half of arc AC plus arc BD. Half of arc AC plus arc BD. Half the sum of the measures of the intercepted arcs. Arc AC plus arc BD. So let's prove this theorem. First, what we're going to do is we're going to draw a convenient line. We're going to draw chord CD. I'm sorry, AD. We've already got CD. Let's draw chord AD. So I'll draw it quickly here. Why can we draw a random line like that? Because through 2 points, there's exactly one line. So if it exists, I can draw it. There's no problem with that. The reason I did that is now I have a triangle, and we know a lot of stuff about triangles. So now I've got this triangle, and to make it easier, I'm going to label the angles so I don't have to call them by letters. I call that angle angle 2, that angle angle 3. So I've got angle 1, angle 2, and angle 3. Okay? Well, in this triangle, angle 1 is an exterior angle. So angle 1 is going to be equal to angle 2 plus angle 3, because an exterior angle equals the sum of the two remote interior angles. The theorem we had last semester. So angle 1 equals angle 2 plus angle 3. But angle 2 and angle 3 are both what kind of angles in this circle? Inscribed angles. Very good. So if angle 2 is an inscribed angle, then angle 2 is half the measure of its intercepted arc. That's arc AC. Half of arc AC. And angle 3 is half the measure of its intercepted arc. Well, angle 3's intercepted arc is BD. Angle 2 is half of AC, arc AC. Angle 3 is half of arc BD. That's because of our theorem that says measure of an inscribed angle equals half the intercepted arc. Okay? But we said angle 1 was angle 2 plus angle 3. So angle 1 then is half of arc AC plus half of arc BD, just by substituting half of AC in for angle 2 and half of BD in for angle 3. So that is the substitution property. That means angle 1 is half of, in parentheses, arc AC plus arc BD, which is simply the distributive property. In reverse, really, but the distributive property. So that I've proven what I want to prove. Angle 1 is half of arc AC plus arc BD. So we don't just come up with that formula out of nowhere. It follows from what we know about inscribed angles and what we know about exterior angles of triangles. Now here's another theorem that deals with other types of angles we could form with circles and chords and secants. The measure of an angle formed by two secants, two tangents, or a secant and a tangent, that are drawn from a point outside a circle is equal to half the difference of the measures of the intercepted arcs. For the two chords inside the circle, we get half the sum of the measures of the intercepted arcs. Here, when we're outside the circle, when the vertex is outside the circle, we have half the difference of the measures of the intercepted arcs. Secants, remember, are just lines that contain chords. So they've got chords, but they extend outside of the circle. So in case 1 here, I've got two secants. The two green lines are my secants. Angle 1 is my angle, which is out. The vertex is outside the circle. So we can apply this theorem, and this theorem would tell us that angle 1 is going to be half of the difference of the two intercepted arcs. And the intercepted arcs are this arc that's x degrees, and this arc that's y degrees. So angle 1 is going to be half of, we're going to take the bigger one minus the smaller one. So x degrees minus y degrees. In case 2, we've got two tangents. Where the vertex is outside the circle, the tangents, remember, just touch the circle on exactly one point. So angle 2 is going to be half the difference of x and y again. Where the two intercepted arcs are that one and that one, x minus y again. In case 3, we've got a secant, a line that cuts through the circle, and a tangent, a line that just touches the circle. They form angle 3, so angle 3 is half of x minus y, because those are the measures of the intercepted arcs, where again, x represents that arc, y represents that arc. So in either one of those three cases, you take the difference of the two arcs and cut it in half. And that's the measure of the angle. We're not going to prove that theorem, but let's look at an example of how to use it. Find the measures of angle 1 and angle 2 in this picture. Angle 1, you'll notice, is inside the circle. Angle 2 is outside the circle. Angle 1 is inside the circle, so that means it's half of the sum of the measures of the intercepted arcs. Well, what are the intercepted arcs here? We've got 70 and 50. Those are the intercepted arcs of angle 1. So we're going to take half of 70 plus 50. Well, 70 plus 50 is 120. And half of 120 is 60. So angle 1 is 60 degrees. Now angle 2 is outside the circle. So angle 2 is going to be half of the difference in the intercepted arcs. Well, what are the intercepted arcs for angle 2? We've got 70 is the big one, and then the 26 is the small one. So angle 2 is going to be 1/2 of 70 minus 26. And 2 is outside the circle, so we take the difference. 70 minus 26 is 44. So we're going to take half of 44. Half of 44 is 22. Angle 2 is 22 degrees. The angle is formed by chords that are inside the circle. You take half of the sum. The angle is formed by secants or tangents, where the vertex is outside the circle. You take half of the difference. So here are your immediate practice problems. Find the measure of angle 1 in problem number 1. Find the measure of angle number 2 in problem number 2. Make sure, for both of these, that you draw the pictures and show your work, or you will not receive full credit. That is the end of section 9.6.